All right, we'll get started. Hello, everyone, and welcome to today's webinar entitled Commissioning Pressure Independent Systems. This presentation is brought to you by Belimo Americas and sponsored by the Western Canadian chapter of the Building Commissioning Association. My name is Craig Hatch. I'm the current president of the Western Canadian chapter. I will be the moderator for today's presentation, and my co-board member, Paul Weaverink, will be leading the question and answer portion of the presentation. Please note that throughout the presentation, all microphones will be muted to minimize any background noise or feedback that may distract from the presentation. We'll be using the Q&A function for questions. So if you have any questions, please submit them through the Q&A function found in the control panel at the bottom of your screen. You can do this at any time. You don't have to wait till the end, the Q&A session, whatever. We'll gather all questions throughout the webinar, and we have time left at the end of the presentation for the speaker to address them. We'll be recording today's webinar for future. Today's presenter is Rick Smith. He's currently the Regional Applications Consultant for Belimo Americas, representing the Northeast region. Rick started at Belimo as a network administrator for the Americas and transferred into field sales and support of Belimo's line of damper actuators and control valves. After 15 years of supporting HVAC controls and mechanical contractors, engineering firms, and end users, Rick assumed the RAC position to offer his assistance in HVAC related applications in regards to product selection, data analytics, and advanced technical training. Rick specializes in the pre and post installation and performance monitoring of Belimo's line of energy saving smart actuators, control valves, and IoT end devices. Rick was instrumental in the creation and maintenance of Belimo's energy valve data analytics analysis tool, which imports data from smart actuators to calculate performance values and energy savings reports. Welcome, Rick.
Oh, you're muted, Rick. Rick is muted.
Rick's muted. There he goes.
Somebody muted me. We're back. So today's presentation is commissioning pressure independent systems, and we've got a lot of content to go through today. And this is basically our agenda. We were asked to present on the following topics, which is what we're going to bring to you today. We're going to take a look at the evolution of the control valve. We're going to look at static versus dynamic balancing. We're going to look at pressure dependent versus pressure independent control valves. We're going to take a look at the anatomy of an electronic pressure independent control valve, and more importantly, commissioning of that electronic pressure independent control valve, the ePIV. Then we were asked to talk a little bit about Belimo's energy valves. So we're going to look at what that basically is made up. We're going to talk about some low delta T syndrome, and then of course commissioning the energy valve, and more importantly, the ability to access and analyze the data that these particular smart valves, they like to be called, actually maintain. We're going to take a look at a couple of case studies, and then of course we'll have the Q&A period. So it's a lot to cover today, but we'll get through it. So we're going to have a poll question here for you. We'll do a quick little poll here, and the poll question is, as you can see on the screen, how often are you seeing pressure independent valves in buildings? And we've got 4 options. I don't have any idea. 25% of the time, 50% of the time, more than 50% of the time. Let's get a feel of what you know about PI control valves. We've got about 10 more seconds left on this polling question. Let's see how we're doing. We're doing pretty good here. Okay, we're going to end the poll. And pretty much, if we share the results with you, I think you can see them now. Looks like we got about 25% of the time is where we're seeing some pressure independent control valves. That's good. The reason I bring that up is I did a quick search in the Canadian regions, and I looked for any projects referencing pressure independent control valves. And you can see right here, a quick search popped up a little over 2,400 projects. And a lot of it's in the specifications is where we are finding PI control. And if you look down here, you can see that there's a high amount of it in educational, government, and medical facilities. So there's a lot of pressure independent control valves out there being specified and putting into projects. That's why we need to make sure we understand them and how to work with them properly. So the evolution of the control valve, we're going to take a look really quickly at pressure dependent systems. And pretty much a pressure dependent system or valve are normally 2 or 3 ways. They need balancing valves or circuit setters to go with them. There's significant amount of effort needed to balance a system. There's a lot of things to do. You just can't set it and forget it. You've got to go through it multiple times to get the right system balance. Pressure deviation, that's the biggest problem with pressure dependent systems, right? As flow changes and pressure changes, that's going to be something that is compatible with each other. Pressures go up and down, flows are going to go up and down. And then we have to size pressure dependent valves. And there's a formula. And the formula is CV, which is the coefficient of flow, equals gallons per minute, which is the design's GPM of a coil, divided by the square root of a delta P. So in order to size a pressure dependent control valve, you've got to need to know a lot of different things. Design of the coil and the pressure differential. That's the pressure differential across the control valve that we need to calculate that. The problem with these systems is they are static. In other words, they're balanced statically. Static is exactly what it says. It's a point, a fixed point. And as you can see down here, this was originally designed for constant flow systems. That's why we used static balancing. In pressure independent systems, you have just 2-way pressure independent control valves. There are no 3 ways. A manual balancing valve or circuit setter is not required. We do not need to use them at all. And pressure deviation in a pressure independent system equals design flow. So as pressures change in a pressure independent system, flow will still remain the same. And to select that valve, unlike pressure dependent valves where we had a formula and we had to worry about pressure differential, all we need to know is the design flow rate of a coil. That's how you select a PI valve. And you get constant flow at part load. And as you see right here, pressure independent systems are dynamic systems, okay? And they were originally designed to be working in variable flow systems where flows are changing constantly. A pressure independent system will set with that flow. When you look at a pressure dependent control valve, as I said before, as system pressures go up and down, the flow through a pressure dependent valve is going to go up and down based upon pressure differential. With a pressure independent control valve, fluctuations in pressure do not affect the flow because the valve will automatically adjust itself dynamically to maintain a constant flow regardless of system differential pressure. That's what makes PI valves so exciting, if you will. What types are they? Well, we have mechanical pressure independent control valves, and pretty much they take a ball valve and they marry it with a pressure regulator like this one right here, or here's a different style of a mechanical pressure independent control valve. But again, it's the same thing. It takes a ball valve and it marries it with a pressure regulator. And then there's another style right here, which again is a ball valve, but this particular type of pressure independent valve uses a cartridge regulator as to a spring and diaphragms regulator, as you see in these two right here. They're using springs and diaphragms. This one uses a cartridge regulator. They all work virtually exactly the same way. So when you talk about mechanical pressure independent control valves, we look at control mode. Now, the first one here is what's called position control. And that's what we're all really familiar with, right? Been around forever. It's really a very simple concept. And a position control relationship, voltage relates to position of the actuator. So on a 0 to 10 volt signal, if you will, it's going to send an actuator to that position in its rotation. So 5 volts would send the actuator to 50% open. Very simple, been used to that for years. In a pressure independent control valve, position control really equals flow control, because in this control mode on a PI valve, when you give it a control signal, the actuator will drive to a calculated flow rate, not a position necessarily, but a calculated flow rate in this rotation based upon that voltage. So you take a look at that. How do we do that? So part of the verification and commissioning of mechanical pressure independent control valves is verification that the valve has actually been set up correctly to achieve the proper design flow. And we can do that a couple different ways, but on mechanical valves, it's normally one of these three ways. There'll either be a mechanical clip position on the actuator, or it might be a mechanical set screw over here that has to be moved, or it could be a dial indicator on a cartridge style type of a PI valve. And all that's doing, like I said before, is it's taking this position, whether it's the clip or the screw, and it gets lined up with a flow rate, which is based upon the design flow rate of the valve. So in this particular case, if I wanted this exact flow rate, I would put it on clip position 3, which would mechanically stop the actuator from opening or the valve from opening to give me that flow rate. That's how we do it. We set a mechanical flow. Now, how do we verify that flow once we're in the field? That's what we really need to do on a mechanical style valve. There's a couple of ways to do it. And you can see here that on this style mechanical valve right here, there are PT ports. We've got 1, 2 here. And maybe you might see a piping package style over here where you've got PT ports that were added onto the valve. But either way, it's the same theory. And pretty much balancing and commissioning agency are looking for a differential pressure across that valve. And it's normally between 5 and 50 PSI. So you can take a pressure reading from the inlet port of the valve to the inlet port of the coil, and or you could take this pressure differential between these two ports. A lot of commissioning people will just walk up to a pressure independent valve, mechanical valve, take this reading across 2 ports, and if there's 5 pounds of pressure differential, they say they're good to go. The valve is ready and it's properly done. But like we said in the one prior to that, you really need to verify that it's been set up properly. What about electronic pressure independent valves? Now it's a little different. In this case, we still take a ball valve, right? We take a standard characterized control valve, but we marry it with an ultrasonic flow meter, okay? So now we have an ultrasonic flow meter, which is connected to a regular ball valve, and it goes to what's called a smart actuator. And they come in different sizes. They go up to 6 inches here. There's also, if you didn't know it, there's also six-way pressure independent control valves. This is a whole nother subject, and that's all in regards to dual temp systems. So how do they work? Well, here's an ultrasonic flow meter, and pretty much you have your fluid flowing through the meter. And basically what we have is a couple of emitters and some acoustical mirrors. So as the water is flowing through the valve, there's also a temperature sensor on the top. What is the temperature sensor for? Well, the temperature sensor is used with that smart actuator to be able to calculate the differences in the temperature for the flow rates and glycol percentage, okay? So what happens is we send a signal from the emitters, which goes through the valve body, and as that water speeds up or slows down, we're basically creating a timing routine between the send and receives, and that's how we're calculating flow. And we're compensating it with the temperature and glycol concentration in the water to make sure we achieve the proper flow rate. So what happens with electronic pressure independent control modes? Well, we still have that position control, but now it doesn't equal flow control anymore like the mechanical one did, right? If we put it in a position, we calculated a flow. With electronic versions, we talked about the sending an actuator to a particular position, but in an electronic PI valve, when we give it a signal, we are no longer sending it to a position, okay? We're sending it to a flow rate, right? So if this was a 10-gallon valve and I sent it a 5-volt signal, I would be telling the valve I want 5 gallons of water, which may or may not be 50% open, okay? So it's a little bit different than a mechanical one because it's an actual flow rate. How do you connect to them to get this information? Well, there are some tools depending upon the style. One was this one right here. You can use this thing. It's called a handheld commissioning tool. And balancers and commissioning engineers love this because they can go up to an electronic PI valve and they can just plug into it with this tool to do some commissioning and verification. You can also connect via a computer and different types of software. Here's the Belimo PC tool software. So this brings up two new terms, which is the most important thing that you need to understand when you're in the field. Electronic pressure independent and mechanical have these two new terms, VNOM and Vmax, okay? VNOM right here is the total capacity and flow that a valve can produce. So the example, a 2-inch PI valve has a maximum flow rate of 100 gallons per minute. That's VNOM is going to be 100 gallons per minute, maximum capacity. Vmax is the maximum flow rate the valve will flow based upon a set point, okay? So let's take an example of that, a coil that has a design flow rating of 80 gallons per minute. The Vmax value is 80, not 100. 100 is the VNOM, the max total amount of flow the valve can produce, but the Vmax is only 80 gallons a minute. So in flow control mode, like we talked about, we said flow control mode says to send a control signal to a valve to a specific flow rate. What an electronic PI valve does is it rescales the control signal to equal the Vmax. Wow. So an example, that 2-inch pressure inlet control valve that had a maximum flow rating of 100 gallons per minute and a control signal of 0 to 10 volts. What do we know about that? Well, we know that the VNOM value is 100 gallons per minute and 0 volts is closed. So that would be 0 gallons and 10 volts would be full open, which means it would be 100 gallons per minute. But if the Vmax value has been set to 80 gallons per minute, or let's say 80%, if you will, now what happens? Well, now the input control signal of 10 volts equals 80 GPM, the Vmax. So now the 0 volts is closed, no flow, and 10 volts equals 80 gallons per minute. See how that changes? So it's very intelligent to rescale its control signal to match the Vmax of the valve. So great question. As a balancer commissioning, why do I need to know all this stuff? Okay. So PI valves do not need to be balanced. There is nothing to balance. Okay. They need to be verified, like I talked about before, and they've got to be properly set up and ready to operate. The control mode will dictate how the valve responds to an analog control signal, right? So based upon the control mode being used, that's going to tell the valve what to do. So position control, like we had talked to, if you're in the field and you're commissioning this valve, you would use position control to verify the valve or the actuator, if you will respond to a full range of signal. So position control, you can give it 0 to 10 volts and it will go to that position in its rotation. Flow control, however, will verify design flow rates at the heat exchanger, whether you're doing a zone or a circuit, okay? So position control can verify that the actuator can fully function. Flow control will verify you're at design, right? Well, how can I do that? Well, one way is with that ZTH tool. And the ZTH tool, when you plug into an electronic PI valve, will allow you to go through a process where you can actually change that Vmax right there in the field, okay, if we're balancing it to a coil. And then you can verify, because it's got that ultrasonic flow meter in it, right on the screen of the tool, that I'm telling it I want, in this case, 89 gallons per minute, and it's getting 89 gallons per minute. So it's really easy to do, and it's right built in. Another way to do it is with software, like I briefly spoke about. And there's a piece of software called the PC tool, and it allows you to go into that smart actuator, and you can set up your control signal. You can change the flow characteristics of the valves from equal percentage to linear. And then, of course, you can go in and you can change that Vmax setting, right there on the screen. So you can use a handheld tool. You can use a software tool to set it up, to verify that it's set up properly. And then on that same software tool, you can also verify that design flow rate is being met. So you can set it check for the flow rates, and right there on the screen, you can verify that the valve is meeting design flow rates like it's supposed to. So the Belimo energy valve, a little different. It's basically a ball valve connected to an actuator with a ultrasonic flow meter, but we add a couple things. We add a couple of temperature sensors, and then we actually gave it network connectivity. So we gave it the ability to communicate over BACnet IP or MSTP or Modbus, etc. So it's a little bit smarter vessel, and I've got a little video here for you that shows you kind of how it works.
This is a Belimo energy valve set up on the return side of a cooling coil. The Belimo energy valve is comprised of a characterized control valve, an ultrasonic flow meter, 2 temperature sensors, and embedded software. The delta T set point in the valve is matching the design delta T of the coil, 15 Fahrenheit, 8 Kelvin. As the temperature sensors detect that the delta T has been below the set point for a few minutes, the valve begins to close to lower the flow. This enables the heat exchanger to optimize the energy output and eliminate the overflow. As the delta T begins to stabilize, the valve starts opening to keep the designed heat exchange output through the coil constant.
And there's the basic operation of a energy valve, which controls and maintains delta T set points to optimize coils for the maximum amount of BTU output they can use. So what are some of the features? Well, some of the features are, of course, the ability to manage delta T with a delta T controller. It's got the ultrasonic flow meter built in. It does glycol monitoring actually inside the valve. It has a nice user interface that you can log into. It also is IoT. It's an IoT-based piece of equipment. It can connect to the internet and connect to a cloud. And of course, it has the ability of data analytics. So what about delta T management? So here's poll question number 2. And let me see if I get this here for you. Okay. The question is, how often, oops, everybody's running on this quick. How often do you think hydronic HVAC systems experience low delta T syndrome? We got some answers coming in really fast here. We're going to give you about another 10 seconds. Okay, let's end the polling and share some results with you. So as you can see, we've got most people say more than 50% of the time, I see this in most HVAC systems. Well, you're pretty much correct. It is very widespread in the industry, and it is a major problem. So, what causes low delta T syndrome? Well, a lot of things cause low delta T syndrome, and right here are just some of the examples. And the bigger ones are right there: oversized chillers, pumps, coils, massively oversized control valves, and piping that wasn't properly configured. Controlling the chilled water valve using only the air sensor, in other words, controlling to an air set point. That's a problem too, and we can talk about that in a different discussion. Manual balancing valves, you only address one flow condition, right? Manual balancing valves are static. They're only set for design flow. We don't live in design load. As this next line says, we live in a part load system. So pretty much what happens is valves are constantly overflowing and underflowing at part load, creating low delta T syndrome. And yeah, hydraulic systems are changed all the time. And do they ever get rebalanced? Normally, no. So let's take a look at some things here. Let's look at a 500-ton chiller plant. And the nice thing to know about flow and delta T is they're inversely proportional, right? So for any given load, when delta T drops, flow has to increase. They are inversely proportional. So here's the math, and I love looking at the math. So if we take a 500-ton chiller plant And you can see here, the formula to get gallons per minute is tons times the constant 24 divided by the delta T. So let's take our 500-ton chiller plant. If we take 500 times the constant 24 divided by a 12-degree design, we need 1,000 gallons of water in order to achieve that. And vice versa, if I want to calculate tons, I can just take GPM divided by the constant 24 divided by the delta T. So the example would be 1,000 gallons of water divided by the constant 24 and 12 degrees equals 500 tons. Perfect. Everything is great. Math is terrific. So plant efficiency is the biggest problem with low delta T syndrome, right? We all know that a plant running at design delta T is much better off than one with low delta T because of flow issues, right? And low delta T can create high flows. Let's look at an example. So we remember the formula, gallons per minute equals tons times 24 divided by the delta T. So let's look at our example. We have got that two 500-ton chillers sitting over here on the side. And I know at design 12 degrees, I'm going to get my 500 tons at 1,000 gallons per minute. But what happens if I drop the delta T to, let's say, 8 degrees, okay? Well, do the math, right? So 500 times 24 divided by 8 says I need 1,500 gallons of water in order to get the 500 tons of cooling. So what did I do? I kicked on a chiller. I didn't kick on a chiller because of my load demand. I kicked on a chiller because of low delta T syndrome, right? And that causes over pumping. And what does it cost when that happens? Well, here's a little example. Take a look at what we've been talking about, that 500 tons of cooling at 12-degree delta T. And you can take a look at what happens if we, say, drop it in half. That's easy math, right? And then we can also take a look that if at 12 degrees of 40% low, we need 400 gallons. At a 6 degree 40% low, we need 800 gallons, right? So when you look at the pump costs of when we're in low delta T syndrome, you can see the difference between 6 and 12 degrees. It only cost me $9,000 to pump at 12 degrees delta T, but look what happens when I drop to 6 degrees. It now costs me 3 times virtually more money to pump. And here's the big problem, right? I ran out of water. I can't even produce that because I don't have more than 1,000 gallons per minute on my pumps, unless some pumps are oversized, right? So not only does it cost us a lot of money, it also takes a hit on our pumps. So we talked about position control and flow control, and the energy valve also uses those two modes of control, but it also introduces another one called power control. Well, what's power control? Power control is basically an algorithm that creates a linear relationship between that 0 to 10 volt control signal and BTUs of thermal output. And pretty much power control will maintain a coil's power set point regardless of pressure temperature fluctuation. So if you've got a system where your chilled water supply, let's say, is fluctuating, right, it's going to change the thermal output. So when we look at it, we have that linear line of our control signal, and we look at our control signal from 0 to 10 volts and our output of our coil. And basically all power control does in an energy valve is take a linear look at the control signal to the BTU power output of the coil. So you can tell an energy valve that I need, I don't know, 100,000 BTUs of power. Power control will automatically adjust the valve to maintain the 1,000 BTUs or 100 BTUs of thermal output automatically for you, regardless of those variances in the supply water temperatures. So it's a pretty interesting feature. So why do I need to know all this? Again, right? We talked about this. We talked about PI valves don't need to be balanced. We talked about the control mode will dictate how it works. We looked at position control, and we said that position control is going to verify the actuator works. Flow control will verify the design flow rates. Power control will verify design thermal output. And like it says, we normally never do this, but you could. It is available to you if you wanted to do that. So an ultrasonic flow meter that's built into the energy valve, basically it gives us true flow because it's the actual flow measure of the water passing through the valve, unlike a calculation. Remember I said a mechanical pressure independent control valve is a calculated flow based upon the position of the actuators, right? Well, in an electronic or an energy valve, it uses an ultrasonic flow meter, so it's the actual water that's flowing through the valve. They're all wet calibrated, so they're completely set up in the factory to make sure that they are set up perfectly, and they have that temperature and glycol compensation built into them. And of course, they provide an added feature, glycol monitoring. So it actually monitors the percentage of glycol in the system, and it uses that information to calculate BTUs and actual flow. So why do we care about glycol metering? Well, pretty much, I think we all kind of know if the glycol content is below our design rate, we've got some potential problems. We can freeze a coil, which is going to cost us a lot of money to repair, and we could damage other components in the building. Oops. And vice versa, if we have too much glycol in the system, that increases the fluid's viscosity, which increases pumping, and we get a degradation in heat transfer, and that might mean that we're not getting the proper amount of cooling or heating to where we need to be. And then, of course, if we just dial that down and get it right where it's supposed to be, then yeah, we can totally increase the overall thermal output. We're going to increase our pumping efficiency, and we're going to reduce our operating costs by a reduction in pumping. So making sure the right glycol percentage in your system is there is a very valuable and efficient thing to do. What about that user interface? Well, the energy valve allows you to connect to it via a computer. And you can just take a standard Cat 5, 6, 7 cable, and you can plug right into that smart actuator. And then you go into a web browser and you type in the default IP address of the valve, and you'll get a pop-up screen that wants a username and password, kind of looks like that. And it'll bring this main screen up, which is going to show you a bunch of live data points. And we'll highlight them here quickly for you. You've got the actual flow rate that's flowing through the valve is on this screen. You have what the DDC set point is, so you can actually see what position the actuator is seeing for a control signal and what position it's in. It'll give you the inlet water temperatures and the outlet water temperatures, and that way we can determine delta T. It also will show you the status of the actuator, that if there's anything wrong with it whatsoever. And it will also, right there on that screen, tell you what the glycol percentage in the water is. So a lot of information is on that main screen. It also has enhanced troubleshooting built into the valve, so you can actually pop a screen up that'll tell you what's going on with the valve and tell you if there's any errors. For instance, here, I got a T2 sensor error, and it will give you the information on that. The one thing I do like about it is commissioning report, and the reason I like it is whenever you commission a system, it's great when you walk away. You can take this particular thing and you can click on the commissioning report. That'll print out a report that is similar to this one here. And I like to take that report. Once I was there, I verified the flow. I verified the valve was working. It was set up properly. And this is the way it is. And I can print this page and I can put it in the book as an as-built, if you will. So it's a great feature to have, or you can take it with you. And then if something goes wrong 3 months later, you can always go back and, hey, here's the printed report when I left the valve compared to what the valve might be set up now. Data analytics, all built into it. The energy valve holds a lot of internal data. It holds 31 days of what we call short-term data files. And what that means is every 60 seconds, it takes about 61 points of information and stores it inside the actuator, and it rolls every 31 days. So every 60 seconds, we're taking a snapshot of what's going on in the valve. It also holds 13 months of long-term data, and it takes that every 2 to 4 hours, depending upon the version of the valve that you have. And that will roll every 13 months. So it stores a lot of information right inside the actuator. And that information can be imported into, for instance, this tool, which is the data analysis tool for Belimo. And the data analysis tools has a lot of different things on it. that can show you exactly what's going on with the valve, how it's working. It actually even will do a return on investment calculation, and it'll actually tell you how much money you're saving by using the valve, because it can calculate how much water would have gone through the valve if the delta T manager, for instance, wasn't activated. So I can tell you how much water would have gone through the valve if I wasn't on, and how much water actually did go through the valve when I was on. And I can show that, and we can put a cost factor on that, right? So we can actually determine a cost savings by taking the data out of the valve and importing it into the tool to crunch all the numbers. You can also access this information right inside the actuator itself. So once you're plugged into it with that LAN cable and you brought that web screen up, you can actually go to the data analytics screen inside the actuator, and you can see all this information like it shows here on the screen. I can show my flow rates, I can show my power output, my delta T's, everything that I want right inside the actuator. So we'll take a quick look at the case study. We're right on time, so I'm glad we're there. We looked at a little case study that was done by a very large tech company in North Carolina. And what they wanted to do was take a look at what happens to thermal output and pumping costs associated with a pressure-dependent valve, a pressure-independent control valve, and then a pressure-independent control valve with that delta T manager installed on it. And what they discovered was, in order to obtain 60 tons of cooling, the pressure-dependent valve had to pump 240 gallons per minute. The PI valve by itself only needed to pump 144 gallons in order to get that output. And the PI valve with delta T manager only needed 96. That's substantial. And we go back to the math, right? And we can calculate this. BTU hours equals the constant 500 times the GPM times the delta T. And if we get our little calculator out up here, and we take a look at that 96 gallons that the delta T manager did, and we do the math, we got 720,000 BTUs out of it. And if we did the PI valve, 144, you can do the same math, and you see it's the same 720, and do the pressure-dependent valve with 240, and you can see it's 720,000. So by using pressure-independent valve technology alone cut the pumping in half from the pressure-dependent. And when we went to PI with delta T management, controlling delta T and thermal output, right? So we're not over pumping a coil. We went all the way down to 96 gallons per minute. That's an incredible and substantial savings. So Ed, you're out there. I'd like you to talk now about a study up at University of Western Ontario.
Can you put the slide up, please?
Oh, sorry.
So good day, everyone. I'm Ed Smith. I'm the district sales manager for Belimo, Canada. I'm based in Calgary, here in Western Canada, and I'm responsible for the Alberta, Saskatchewan, Manitoba regions. I'd like to provide a brief overview of the success story here in Canada, which focused on the implementation of the Belimo energy valve at the Western University in Ontario. The university has a population of 40,000 students, faculty, and staff, and the campus has a mix of Gothic-style buildings and state-of-the-art LEED certified buildings. The utility costs average over 20 million Canadian dollars per year. And the focus of this particular project was for the improved performance of the chiller plant operation. So what Rick was talking about previously here. They replaced the control valves on the air handling units with 223 energy valves. This optimized the delta T by 5.3 degrees Fahrenheit. That's an improvement of 5.3 degrees. It improved the system performance, reduced pumping by 4,942 GPM, and increased the occupant comfort. As a result of the peak energy demand costs were reduced by 6.5 million Canadian over 3 years. So tremendous savings through their energy costs. If you want, there's further details for the project can be found on the case study paper on our website. And we're going to send out a link to everyone in a follow-up email. Next slide, please. So Belimo, we've got a lot of additional resources. We got online Belimo University courses. We got PDH courses. We have webinars, YouTube videos, and along the bottom of the screen here, there's links to all of those additional resources. And just one more slide, I believe. This is a list of the PDU and PDH courses that are available. And again, we'll send this list out to everybody in the follow-up email. And I think that's, yeah, and also a commissioning process document. We'll send this out, a brief overview of the commissioning process for mechanical and electronic PI valves. And I think that's it. So as a follow-up to the Tech Talk, we'll be sending out an email to everybody who attended with a link to the case study, the list of the PDH, PDU courses, and a copy of the commissioning process. So now I'll turn it back to Craig to moderate any questions that may have come in, and I appreciate your time and attention. Thank you.
All right, thanks, Ed, and thanks, Rick, for the presentation. As Ed said, now we'll address some of the questions from the audience, and Paul, lead on with the questions.
Okay, got quite a few questions, so I've been writing a few of them down, so we won't be able to answer all of them here, but I believe Rick will be able to answer everything after the webinar. So first one I have, okay, who will normally have the ZTH tool or software to communicate with the valve? What specific training is needed? And I think that probably comes from maybe a balancing commissioning company. Like what's the investment needed to actually do the verifications of these systems?
Good question. The tool normally would be obtained from a local district sales manager, a Belimo local district sales manager. And that person, you can find who they are right on our website just by typing in your particular location. And the training to it is 5 minutes maybe tops on how to plug it in or go through the screen. So there's really not a lot there. And they're not a high price point tool if you have to purchase one. And that's just something that you would work out with that district sales manager.
Okay. Another question. Are the temperature and flow readings available via the BMS as separate values, or is this just information used within the valve assembly? So I think the idea is to tie it all into the BMS system, have flow monitoring, control, lots of points on the BMS.
Yeah, so if you've got BACnet, you can bring in 60 something points of information. If you don't have BACnet, the energy valve has a single feedback wire. That feedback wire can be programmed to bring back one value to the BMS, one only, and it could be flow, it could be delta T, it could be BTU output. So you've got two ways there, BACnet, of course, being the best. And again, it's BACnet over IP or BACnet over MSTP, and that you can bring everything back. But you don't have to bring any of it back. You could just go to the valve and plug into it and get all that information.
Okay. Okay, there was a few questions regarding this, and that's the accuracy of the flow meter over time. So I'll just ask the direct question. Is the accuracy of the ePIV ultrasonic flow meter affected by corrosion or deposits inside the meter?
No, that's one nice thing about it. It's a very high quality. It's plus or minus 2% accuracy with a 2% repeatability. There's absolutely no maintenance required on the meter whatsoever, and it's not affected by dirty water or anything like that, which is one reason why we went. Originally, we used magnetic flow meters. And there were issues with magnetic flow meters in regards to some of those examples, but the ultrasonic is much more sophisticated and has a much better tolerance to that type of issues.
Okay. We had an email question. Actually, we briefly discussed it before the webinar, Rick, and it was a complicated question that may take some time, but I think we have the time. And the question was, what's the added pressure drop to your system and the potential operational cost penalties?
Okay, Uh, Actually, you're going to have a reduction in your overall system pressures because with any pressure independent control valve, they're going to maintain constant flow regardless of pressure differentials. So in a standard system under, let's say, part load applications where pressures are going up and down, flow through those valves are going up and down, which is affecting overflow in, let's say, coil A and then coil B, et cetera. So when you go PI, we're no longer going to allow overflow. That's not going to happen. So that water that would have gone through that one coil now isn't going through that coil, it's being pushed downstream. So we just keep pushing downstream, right? Because we're not allowing overflow in any of our coils. So that's going to bring down our overall pumping because we won't need to be pumping as much water, which is going to change our system differential. So in reality, you're reducing flow and maintaining a more stable pressure differential across your system compared to pressure dependent control valves, which will constantly go up and down with flows and pressures. I hope that answered it.
Okay, great. Go to the first question. Verifying DP does not verify the valve is providing the required flow. This causes us to require tab contractors to install ultrasonic flow meters. How do you verify the actual flow rather than the required DP? That would be in the case where you don't have the ultrasonic flow meter. So I think the question is, you've got this valve. We're trusting that the manufacturing process and the testing, that once that valve is set to a certain amount and that delta P is being maintained, you're guaranteeing the accuracy of that valve. Did I just answer the question?
Yeah, on the mechanical pressure independent control valves, right? Because the electronic, obviously, you have the ultrasonic flow meter built into it, you plug into it. But on the mechanical ones, as long as you're maintaining that differential pressure across the valve to allow the regulator to work, it will maintain consistent flow. The problem only comes in if you don't have enough pressure under the 5 PSI or over the 50 PSI. That's when the valve kind of turns into a regular everyday pressure dependent control valve. We like to have on that one screen shed, you can verify flow just like you do with any pressure dependent valve by taking the pressure points across the coil and do the calculation that way. Or what happens, and I hate to say this, and I said it during the presentation, a lot of people will come in and go, oh, it's a mechanical PI valve. Let me just check the pressure differential across the valve. Oh, I've got 6 pounds. You're good to go. Everything is fine. But they didn't do some key things, which I hope I pointed out, verifying that the valve is actually set to the right flow rate, right? So it could be a 10-gallon valve and it's supposed to only be 6 gallons, but it's set at 10, and you come up and put your DP across it and you've got your 6 PSI and you say, hey, I'm good to go. Well, you're good to go at 10 gallons, not 6.
Okay.
That's why this is important to know.
I'm going to ask a combination of questions, and it's maybe a little bit of a complicated answer.
Okay.
What's the payback on these valves? Also, what's the most efficient? You know, if you have a limited budget, obviously there's a cost increase to your project for these valves. Where's the best place for them? Where's the best bang for the buck, and what's the payback?
Well, payback can be calculated, especially with the energy valve, because all the data is being maintained in the valve. So you can just get that data and it'll show you the payback. But pretty much PI valves should be system-wide because they don't allow overflow. Electronic PI valves and energy valves, normally you want to see them on all your air handler units. You can go all the way down. So we have mechanical PI valves. Well, the industry has mechanical PI valves that go all the way down to a half a gallon. So you can put those on VAV boxes. You can put them on the reheat. You can put them on, I've got them on perimeter radiation. I mean, everywhere you put a PI valve is going to help stabilize and make your system a dynamic system as opposed to a static system. So the answer really is everywhere. On any end device should be a pressure independent control valve. But if you are on that limited basis and you want to hit the meat, it's all your air handler units, your heat exchangers, especially any air handler unit over 30 gallons per minute.
Okay, fair enough. I'm just going down. There's a lot of questions. I'm just going to have to randomly pick short ones.
Sure.
Here's one. If the energy valve maintains a constant delta T, how does it control space temperature at part load design delta T may overheat or cool the space? I apologize.
I'm guessing that's somebody with maybe a controls contractor background. A key thing you got to remember about the energy valve and low delta T syndrome is pretty simple. Basically, all that's happening in the valve is you've got a coil designed at 100 gallons per minute at a 12-degree delta T. All delta T manager is doing is sitting there looking at the flow rate through the coil in the delta T. And it sees, as we talked about it, flow and delta T are inversely proportional. So let's say you've got an energy valve in a room and all these people run it and I need more cooling. Well, what's the BMS going to do? The BMS is going to say, hey, open the valve. I need more cooling, right? So all delta T manager is sitting there going, hey, I understand you want more cooling, but I also understand if I give it to you, you're not going to obtain any additional thermal output, right? So all we're doing is watching the delta T, and once the delta T drops below 2 degrees for 5 minutes, the actuator takes control over the BMS system and brings the delta T back by reducing flow, right? So we're not allowing over pumping. Now, you've got to remember there is a water side and there's an air side, and that's where there seems to be a little bit of a discrepancy. All we're doing is maintaining the maximum thermal output of a water, right? That's what we're doing. That has no effect on the supply air temperature because we're maximizing the thermal output, the design of that coil. And the design of that coil is set to your set point. So that's why we've never violated supply air temperature. All we're doing is not allowing overflow because we know if I give it to you, you're not going to get any more thermal output. You're just going to increase pumping costs.
Okay, good answer. What is your size range of your valve and flow rate meter combination?
0.5 to 713 gallons per minute. And for coils larger than 713 gallons per minute, we have multiple installations where we're using 2 to 3, either a combination of energy valves or energy valves and if you saw before, the ePIV, just an electronic pressure independent control valve. So we can go pretty large.
Okay. Okay. Where do these valves really shine? Zone, building, HU applications, or something other, or everything?
Everything. I mean, we have them controlling loops. We have them controlling floors off of risers, for instance. Heat exchangers are a big one. I'm controlling heat exchangers based upon delta T, not even a control signal. I just got an energy valve hooked up to a heat exchanger with the design flow rate and delta T, and it's running by itself. So they really can be put in a lot of different applications. It all depending upon what you're trying to accomplish and how much energy you're trying to save. And that's what your district sales manager is and your regional application control specialist. Jenna Lyons, for instance, in Canada, that's what they're there to help you with. You can always contact them and go, hey, I've got this application. What do you think? What do you think I'm going to get out of it? Is it going to function properly for me, et cetera? And that's what they're there to help you with.
Okay. So here's a question. Do you see lots of projects with mixed pressure independent valves and pressure dependent valves?
All the time.
All the time.
You don't have to go in a building and just change the whole building out. That you don't. I would love you to, but you don't have to. The key thing is every time you put in one pressure independent control valve and rip out that old balancing valve in the circuit setter, which is a pressure drop in itself, right? Okay. Yeah. Once you put that one in, you just save pumping costs on that one end device. So as you continuously put more in, you are continuously reducing your overall pumping. So I have a lot of buildings that are done in stages. It's great if you can do a zone at a time. Or a floor at a time, something like that, and then keep working your way that. But yeah, a lot of combinations where we just have pressure independent on all the big stuff, all the major air handlers, and we're running PD, pressure dependent on the VAV boxes, the reheats, the perimeter radiation, but you're looking at such low flow rates, right? It's not a big deal. We actually have pressure independent technology for controlling chilled beams and dual temp water systems. That 6-way valve you see on the screen right there, that's a pressure independent because it has an ultrasonic flow meter attached to the 6-way valve to control flow on chilled beams.
Wow, okay. So the best thing is to just, well, contact your local sales rep, discuss your project, and they'll probably give you the best recommendation of where the money is best spent.
Correct. I like to take a look at the whole project, and then if I am working with a budget, or a lot of times it comes down to, hey, I cannot control this air handler. I just can't control it. It's running amok. It's a mess.
Right.
Those are really the ones that we want to go attack because we can fix them.
I see a question here. Cost savings, can these valves be deployed in a main branch serving a group of terminal units and have regular pressure dependent valves at each unit? Now, I guess in a case of 2-way valves, that might not work because your one pressure independent valve would always be trying to maintain that pressure, and valves downstream could be closing. So maybe that wouldn't be a good application.
It's not pressure, it's flow.
It's flow, right.
Okay. So I think the question was, can I put a PI valve on a loop that has multiple pressure dependent control valves in it? Was that it?
Yeah.
Yeah, so the simple answer, what you would do in that particular application is make sure the loop would never overflow from design. However, unless it's piped in reverse for turn for all the terminal units, you're still going to be overflowing the ones closest to the pump, right? You have no control. If you're not reverse for turn, that's going to happen.
Right.
Even if there's circuit setters on each terminal unit, because remember, we're going to go back to part load, right? And if we're going to part load, we're going to overflow the ones closest to the pump. So it'll make sure that you'll never overflow the loop, but it's not really going to do a whole lot for optimizing the actual terminal. I always say work from the terminal units back to the chiller plant or the boiler.
Okay, and I think given the time, we'll ask one more question.
Sure.
How is the DDC control signal and valve controller coordinated, i.e. how to avoid the DDC signal hunting while the valve controller lags actual controlling the valve? Does that make sense?
In an old pneumatics world, yeah, definitely. Typically, most DDC systems, there's really no major hysteresis or lag time in the actuator responding to a control signal. If the control signal is bouncing, fluctuating, 3 volts, 3.5, 3.2, 3.7, et cetera, things like that, that's a little bit different story because you're in a pressure independent valve. Remember, you're telling the valve, I want a specific flow. So if you send it that signal, you're saying, I want this amount of flow going through the valve. And it will sit there. So, but as you change the BMS signal, and if you do have hunting scenarios, that's another nice thing about the energy valve. It's going to tell you that. The energy valve in its data will tell you, you have a problem with the BMS. You're hunting too much. So that's another good thing about these valves is they're also a heartbeat of the system because of the data that they take. You can once you put energy valves in, you can find out what's wrong with your system real fast.
Right. Okay. We can go a little bit longer on the questions. I know some people are probably sign off at 10 o'clock, but we're up now. I don't know, Craig, do you want to give the kind of the closing comments for the people that are signing off at 10, and then we'll stay online to continue with questions?
You can keep going, Paul, and then if you just give the closing at the end.
Okay.
Essentially, a summary for anyone that needs to take off is, sorry, I know I said no. Thanks, Rick. Questions, you can email him. His email address is on the screen there, rick.smith@us.belimo.com. Soon after the presentation ends, you're going to get a survey from Belimo. Take a moment and provide any feedback. And if your question wasn't answered, Rick or Jenna are gonna try and get back to you guys with answers in a short period of time. And as Paul said, if for those sticking around, we have about 10 or 15 more minutes for some more questions.
Okay, I'm going to go back to the top because I was just kind of picking random questions. Okay, that's that. Okay, this is a technical question. Is there authentication for the IoT connection? Are there special network requirements, IG holes and firewall, or additional web server, etc., for the valves to connect?
No, it's a standard IP address. It comes with a default address of 192.168.1.10, which obviously is can be changed inside the actuator, but no, any standard IP LAN is fine. I mean, if you've got a plug through firewalls, etc., that would be something on your internal IT department, but there's nothing special about it. It's just an IT device, just like anything else.
Okay, next one's a bit of a longer one. ZTH tool depends on the accuracy of its ultrasound. With this specific tool, we have had the ultrasound in the valve disagree with what other independent flow measuring verifications performed. Is there a rule for installation of the valve, as we have seen other components installed adjacent to the PIC valves that may affect accuracy? So obviously they need laminar flow. There's installation guidelines. Maybe I'll let you elaborate on that, Rick?
Yeah, the only installation guideline on an electronic PI valve is it requires 5 pipe diameters of straight unobstructed pipe coming into the flow meter. Going out of the flow meter, you can run a 90. So unlike most ultrasonic flow meters, magnetic flow meters, etc., where you need 8 to 10 in, 10 to 12 out, we don't need that whatsoever. The flow meter is so calibrated that we only need that 5 pipe diameters in. And I've actually seen isolation valves put right on the inlet of my flow meter, butterfly isolation valves, and even with the wafer, with the water going around that wafer going right into the flow meter, it's a nominal reduction in the accuracy of the flow meter. So no, that's the only limitation is the 5 pipe diameters in. And you got to remember, we're compensating, if you've got glycol, and you're looking at, let's say, a independent flow meter compared to our ultrasonic internal flow meter, and you've got glycol, we're compensating for the glycol compensation in the flow calculation and the BTU calculation. And if you throw a strap-on ultrasonic on a pipe compared to an internal ultrasonic, they're never going to match. Right? It's not going to happen because an ultrasonic flow meter strapped onto a pipe, it's got a whole lot of things you got to do. I got to know pipe thickness. I got to know pipe material. I don't know how much scale or sludge or crap is inside that pipe that I'm trying to read through. So when you got to be very careful when you look at things like that. And then where did you install that ultrasonic flow meter, right? That you strapped on. Now that's why we don't allow strap-ons. People have been asking us for years, can you give us a strap-on option? No, for temperature sensors and for a flow meter to be connected to the smart actuator. No, because it's just not accurate enough.
It's funny, speaking from experience, I'm with you 100% on that, Rick.
Yeah.
It's not even an option. I mean, there's so many variables that you have to input. You would never be able to verify the accuracy.
Right. And then you got to calibrate that strap-on flow meter that you're carrying around in a box and dropping in your back seat and just took out of the trunk of your car at
Exactly.
22 degrees.
Okay, here's another one. The Venturi effect does increase the flow velocity through the meter orifice, but is there a bad initial flushing? If there is a bad initial flushing procedure, then is it a fouling potential? There's a lot of concern about, these things over time in the fouling, but you seem to be very confident that that's not an issue.
No, we haven't had any. Again, one of the reasons this is a patented flow meter from Belimo. We had in the past, we're using other manufacturers, and we learned a lot of lessons doing that. Hence, we had to design our own. And some of those are exactly the questions that are being asked right here about over time, what happens with water quality, scaling, that initial flush. You see a lot of especially cartridge-based mechanical PI valves, where you can't have that cartridge installed when you're first bringing the system online, right? It's got to be removed so that you can flush and then you put it back in. With this technology, we don't have any of those. There's nothing that's going to get corroded in there. So the water just moves free flow it, and it can read in very dense conditions.
And I'm going to ask, just confirm my own question. It's very important that somebody verifies proper setup of all these valves. I mean, I know balancers, the idea is to save a lot of money. Well, these are all pressure independent valves. We don't need balancing. The balancer does what he's paid to do. But there does need to be a verification process of some sort, or these things are only as good as the design spec, I suppose.
Exactly. It's one of my pet peeves, if you will. That's why I've been pushing in the United States engineering firms to adapt some of the verbiage that is in that one slide that I put up that people can download. Oops, this one right here. I've been pushing a lot with major engineering firms in New York City and Philadelphia, et cetera, to add this in as a specific process. Because yeah, I've been on many a job where I'll get a phone call, you know, why do I have to ramp my pumps up so high? This isn't the way it was designed. These are all PI valves. What's going on here? And that's when I'll go out and I will find that condition I talked about. The valve was only supposed to be 6 gallons per minute, but no one either A, ordered it to be 6 gallons and it came out 10 gallons, or no one bothered to change it to 6 gallons. So you balanced it by checking the DP across the valve and hey, it's working, everything is good. But if you don't check to make sure it's set up right, and the other problem is most valves are shipped out in position control. If they're in position control, that means they're a normal, everyday, pressure-dependent control valve, period. If they didn't change it to flow control, it's not pressure independent. So an electronic version of the valve is someone didn't, or let's say an agent came out and said, let's verify that the actuator moves full stroke. So they put it in position control and they ran it full stroke, but then they didn't put it back in flow control. It's no longer a PI valve anymore, right?
Right.
So you're going to get overflowing and underflowing. I'm going to get the phone call. So I think this is incredibly important that this should be added. And it can be added in a couple different places in the specifications. It can be in the TAB, or it can be actually in the engineering specs for the job under the commissioning process. But I think it's very important. I agree with you 100%.
Yeah, and I've seen in the case of cartridge type valves, you're very dependent on the right cartridge being put in. Once that cartridge is in, you're not going to pull it out and check it.
Correct.
It is an issue. I mean, we see it more and more.
Yep.
Let's see. There's more questions about glycol. Sorry, it's just taking some time going through.
No, I'm in no rush.
Yeah.
I told you, I got all afternoon.
Okay.
I'd rather be on a job site, but I can't do that.
Yeah, exactly.
They won't let me.
Some thank yous here. Oh, here's one. Would you recommend circuit setters installed on return lines from a building to help with valve authority in a campus loop system?
Again, it's a static product, and it's only designed to attempt to not allow overflow at design. It has nothing to do with part load. So your answer could be yes, if I want to see if I can stop the overflow of a building loop on a main campus. But in reality, that building isn't running at design. I highly doubt it anyway. It's running at part load, which means that balancing valve is doing nothing for you. It's not doing anything for valve authority to all the end devices inside the building. Do we put PI valves in buildings for design? Yeah. I have a building in Massachusetts where the entire building is being monitored for flow control. And instead of using differential pressure to set the pump speeds, we're using flow, right? So we no longer care about differential pressure to manage our pumps. We're actually looking at the flow rate going through every single valve in that building. And that's what's telling the pump how much it needs to pump. So you can do the same thing on a building loop. You can look at what all the valves in the building are calling for, and you can adjust that PI valve to maintain that loop flow. Does that make sense?
Yeah, yeah.
Yeah, it's a little bit more work. Can you do it with position control on pressure dependent valves? We've had people do that, sort of like VAV polling, right? Sort of the same thing, but you're doing it on a water side where you're actually maybe polling an actuator to see what position it is and calculating a flow and adjusting the valve to compensate for that. So yeah, the answer is yes. Well, the answer is no. Don't use a balancing valve on a loop control, but you could do a lot better things using a PI valve on loop control or building control.
Okay, I think this is going to be that was going to be the last question.
Oh, okay.
More time. I want to thank you very much, Rick. This has been a great presentation, and I want to thank all the attendees. I mean, this was almost record attendance for one of our webinars. So I hope everybody learned something and got something out of it. Craig, I don't know if you have anything more to say. Craig's still there. But if that's it, once again, thank you for everyone for joining this. And thanks again to Belimo and our presenters.
Thanks for having us. Hope we can do some more. Okay, take care.
Take care.